Okay, so we are going to, the first topic we are going to study is waves. And in particular, waves is a very common motion in continuous systems. Okay, so in your earlier classical mechanics course, classical mechanics 1, for example, you have focus on point masses, or a system of point masses. And in this course, we'll start to study continuous systems. Continuous systems, you can think of them as infinitely many very small masses. Okay, so the number of degree of freedoms will be infinite. And the system, the motion of continuous systems will be governed by partial differential equations, not surprisingly. Okay, so wave motion is a common feature of continuous systems, and it's a common way to transmit energy. And the wave equation is one of the most important and fundamental equations in physics. So we will be mainly dealing with a common form of wave equation. I think we'll basically use the one dimension most of the time for the illustration, but the general wave equation is in 3 dimensions. And the common form of wave equation that we are going to see a lot is this equations. So it's of this form of the Laplacian of certain function. This function is a space of space and time. Space, this vector r, 3-dimensional in general, and time t. And it is equals to some constant I call 1/c squared here, times the second order partial derivative of that function with respect to time. Okay, so this is a very general equation that you commonly see in physics, but you should understand that this is not the only wave equation. Obviously, wave equation is the equation that governs this so-called wave motion, or the transmission of disturbance or energy. And this is not the only equation. In particular, this is linear, as you can see. Well, this is a linear equation, meaning the derivative here, the Laplacian and the second order partial derivative with respect to time, they all appear in just linear power one power. Okay, but you should know that there are other forms of more general wave equation. We'll come to them a bit, or at least mention them as we go along the course. And this function phi can be rather general, and it is some this is usually the amplitude of some disturbance. And as this disturbance will be in this continuous system, which occupies a certain region of space, and so it will be as a function of position. Usually will be 3 dimension. It depends on the situation. Can be approximately 1 dimension or 2 dimensions, and then also time. So the function, this disturbance or this amplitude of the disturbance is naturally a function of more than one variable. And so the equation governing it will be a partial differential equation. Okay, then if you just look at the dimension of the equations, this side you have 2, the left-hand side you have 2, it's a Laplacian, so it's a second order, the dimension is this phi divided by a length square. So on this partial derivative of phi, second order partial derivative of phi with respect to time, then it will be 1/time square. So the 2 sides has to have the same dimension, so you must have some constant of the dimension 1/a speed square to relate them. Okay, so c square here is of the dimension of c also is of the dimension of speed, and as you learned from your previous course, like in the physics 3051, then you can see that it is actually in this particular case for this equation, this wave equation, this c is indeed the speed of the wave, or the speed of the transmission and propagation of the disturbance. Okay, so we will be going to derive this equation for the special case of the vibration of the string. You should have already seen this before if you have taken my physics 3051 course. But today we're going to derive it again, but this time we'll go deeper and try to, but the usual deviation will be confined to small displacement, small vibration of small displacement. But we are going to relax that particular assumption and consider the case of general displacement, not only small displacement, and we'll see whether the equation will change or not. Okay, so we will talk about the string vibration later in details to derive this wave equation. And there are other cases that you will also see this wave equation, but not in the context of vibration of string. So vibration of string is just a easy starting point for us, but you should not just restrict you should not restrict the thinking to just vibration of string. Actually, we're going to use that as an example to see the properties of wave motion, how we want to know how energy is being transmitted. So we need to know, and also what happens when the wave will hit some boundaries, the reflection, transmission, and also the more general situation of dispersion, not for this particular case, but we will also study dispersion of waves. And in this, also we'll learn about the Lagrangian formulation of continuous system and use it to derive the wave equation again. So all this will be covered in this chapter. Okay, but another case you see this wave equation again will be in your EM course. So in particular, one can derive the, well, we know that the electromagnetic waves, well, obviously EM waves is a wave, okay? The propagation of the EM waves is governed by the same form of the equation, and with this phi being the electric field or the magnetic field, okay? So that equation, the equation for electromagnetic waves can be derived from Maxwell's equations for, well, the easiest way to see this is from the case in vacuum. So that will be either reviewed or shown to you in exercise class next week. So in exercise class next week, the teaching assistant will derive the wave equation in two more contexts, not well, other than the vibration of string. And waves, of course, can be either transverse or longitudinal, in the sense that transverse will be perpendicular to the disturbance. The direction of the disturbance will be perpendicular to the direction of the wave motion. That will be the case for the string. And it can also have longitudinal waves that the disturbance will, the direction will be parallel to the direction of wave motion in the case of like sound waves or pressure or density waves. And you compress or relax, compress or affect the material. Okay, so that's so much for the introduction. And now we're going to derive the wave equation for the string, okay? So here, because you should have seen it before, I'll be a bit, I'll just use the PDF outline here, show you. And then later I want to derive it for more general case of not only for small displacement, and I'll turn to the whiteboard to show you. Okay, so let's set up the problem first. So we consider a string, okay, one-dimensional. This string has constant linear mass density, that is mass per unit length, denote it with this symbol rho. And the string is being stretched, it's under tension, okay? And in equilibrium, when it doesn't, you don't disturb the string, it will lies along a certain well, axis. I call it x-axis. You can think of it lies on your well, table. Well, doesn't matter. It's lying on x-axis. Okay, and then we only restrict the vibration to be perpendicular or in the transverse direction to the string. So that will be the situation. So the string originally may be here, and then you let it vibrate in the direction that is perpendicular to x. So I call this perpendicular direction, the y direction. So in the y direction, okay? So the string can be vibrating in the y direction, which is perpendicular to the x direction. And so let's see how we should derive this, okay? So you should have seen this before, so let's just review this again. So because the string is now, this is an example of a continuous system. It consists of many, many masses, right? Point masses connecting all together, right? So we can just focus on a small segment. Okay, this is a small segment. Well, this is not very small in this figure, well, because we need to show you clearly, right? But you should imagine this is a really small segment in size. I call it delta x. So x from x to x plus delta x. So I focus on this small segment. This is originally lying horizontally here, and then when it is stretched and vibrating, when it is vibrating, so it will be moved up. Okay, here. So let's say the angle, this particular point x plus delta x mixed with the x-axis is theta 2, and the angle that this point x, the string as point x is mixed with the x-axis is theta 1. Okay, so you look at, essentially just apply Newton's second law to this segment. Okay, you look at the forces acting in the y direction, because we only allow the string to move in the y direction. The vibration is only in the transverse direction. And then you can see that, this is the tension T, and the direction along, the component along the y direction with T sine theta 2. And similarly, this will be T sine theta 1, but in the negative y direction. When theta and 2 and theta 1 are less than pi over 2, well, we consider them to be small, so small. Okay, so the depth force acting on this segment will be T sine theta 2 minus T sine theta 1, and it has to be equal to the mass, which is the rho, the mass density per unit, the mass per unit length, times delta x. So it's rho delta x, and then the acceleration of this segment, which is described by this u, right? This is displacement, I denote as u second order partial derivative of u with respect to time. Okay, so this is exactly what we have here. So we will have rho delta x utt equals to this T sine theta 2 minus T sine theta 1. Okay, so you can see that I already taken the tension to be the same at both points. So you see later, I will show clearly later that this is not an additional assumption. This constant, the tension being constant, T being constant, is a consequence of the assumption that the vibration is in the transverse direction only, and the displacements are small. Okay, so I will show you this more clearly later. So T being constant is not an additional assumption. And anyway, so let's continue here. So that's the assumption. Now you see we use the approximation that the displacement is small. But displacement small means this angle small, so sine theta is just approximately tangent theta. So, so we have this, and tangent theta is just the partial derivative of u with respect to x. Okay. By the way, about the notation, I use the subscript to subscript x to represent the partial derivative with respect to x. So that will be the notation we have here for the partial derivative. Okay, so t here, and we've got here. And so we put them all together. So that will be the second law, Newton's second law applying to that segment. And we get this. Okay, so then final step will be we take this delta x to be 0. Okay, so that's the standard technique of deriving equation of motion for a continuous system. We look at a small segment, delta x, and then eventually let it go to 0. So we will see this trick many, many times later, particularly also in deriving equations for fluid motion. In that case, we will take a small region, or we call it a full element in delta volume. Okay. In any case, so let delta x tends to 0, then you put delta x to the other side. You see this is just when delta x tends to 0, then the right-hand side will become the partial derivative of ux with respect to x. So it's uxx, okay? And I put all the things together, then this is rho there. Well, the uxx on this side and then utt. So put t to the other side. The rho over t will be 1 over rho over t on this side. And that will be my 1 over c squared. So c is square root of t over rho. Okay, so that's I intend to make this very fast, but because you have seen this before. But in any case, let me stop for 1 second to see whether there's any question. Okay, so feel free to let me know if you have questions, or either put up a chat or raise your hand. Okay, so now we got this. Okay, so that's the equation. So remember, this is obviously exactly the same form that we've seen before. And in this case, this disturbance or the amplitude will be this displacement of the string measured from its equilibrium position. I use this notation U. Okay, so now let me switch to the, well, okay, I'll just continue with this equation and then I'll switch to the whiteboard to explain. Okay, so I told you that they have, well, we have, what are the assumptions made in deriving this equation, this wave equation? We assume, obviously, we assume the theta to be small, so it's small displacement. Okay, and another will be we only restrict, we only allow the vibration to be in the transverse direction. Okay, so these are the two assumptions: small displacement and vibration only in the transverse direction. So now we are going to see that these two assumptions will automatically give you a constant tension. Okay, so but let's just remember this figure. Okay, let me turn to the whiteboard. Okay. Okay. Yep, there's a hand raised, it seems, right? Let me see. Okay, but okay, probably is by mistake because I don't see any hand raised now. Any question? Okay, no. So I want to show you explicitly that yt has to be a constant if we take this assumption. So let's see. So remember that's the string, right? We have t theta 2 here and theta 1 here. Well, actually, it doesn't matter. So suppose this t is not a constant, it's a function of position. So now we have to remember this. Well, this is my x, and this is my x plus delta x, right? So t here should now be a function of x plus delta x. But in general, it can also be a function of t. Well, you may think, but let's just make it very general. And then this is t x t with the tension, right? I use this. The tension can be a function of position. Okay. And now I want to show you this. Trying to get my notes. In any case, so let's just look at the horizontal, the force in the horizontal, I mean in the x direction, because there's no we do not allow motion in the x direction. So all forces in the x direction must cancel. The net force in the x direction must be 0. So let's just look at the, well, we all know so this is cosine theta 2, and that is in this direction. direction, but this, okay, this should be, well, we are thinking about, okay, let me do it here. We're thinking about this component. Well, I want to use different color. Well, so that's the segment I'm interested in. And so the force acting on it, this will be due to the tension from the other remaining part of, I mean, the part of the string on the left hand side, and this is just part of the string on the right hand side. So they are pointing in this direction. So the tension, the force acting on this blue segment along the x direction will be tx plus delta xt cosine theta 2 minus tx t cosine theta 1. And that has to be 0. The reason is because there are no, there are only transverse motion, no longitudinal motion. So this is exactly this is longitudinal motion. There's no longitudinal motion. Okay. And so that means, and now we want to get the cosine theta. Well, we have to, but okay, but the cosine, but the we restrict, well, remember we are saying that it is small displacement, right? Small displacement, so let's just small displacement. So both theta 2 and theta, cosine theta 2 and cosine theta 1, approximately 1, because it's small theta. So we have this tx plus delta xt approximately txt, or I should just say minus t approximately equal to 0. In other words, we will have 1t, 1x being 0. Okay, so that follows from this the assumption there's no longitudinal motion and small displacement. And so txt must just be some function of t. And but think about why there should be any time dependence. Well, this time dependence must be only this function must be only a function of the material properties, the elastic properties of the string. And for most of the case, well, usually, well, you will not, the string is given to you, there's no change in the material properties. So there's no time dependence from there. So in other words, that has to be a constant. And so this is just, so again, let me just write it clear here. So this has to be only a function of material properties. And for, if the string is given to you, there's no change, then that has to, that will be independent of time. For a given string, unless you have a situation that the string, the material properties will change with time. You can have such situation. Imagine that situation occurs, but for a given string to, I give a string to you and study its vibrational motion, that will not be the case. And so that in that case, this ft will be just a constant. So what we have shown that if there's no longitudinal motion and also small displacement, then this tension has to be constant. And so tension is a constant. Okay. Okay, is it clear about this derivation? Okay, so now let's turn back. I want to move back to the notes, and then you will see we now want to relax one of the approximation, which is the small displacement. Okay, so now I want to derive the wave equation or the equation of motion of the vibration of the string for the general case. That is, I don't restrict to small displacements. So I want to pause this out. Well, maybe I should. So now I want to pause this out. No more small displacement. And then I would like you to think about it. So what will change? Okay. So before we move on, well, if you have not read the notes, you probably can, well, even if you read the notes, it's okay, you know the answer. But let's just see. Okay. Cannot move the screen for some reason. I see. Okay, okay. That's strange. Yeah, of course. So let me just clear it. So I want to cross that out, as you know. I want to relax the relax the small displacement assumption, and I want to see whether what will change. So let me have a show of hand. So the equation of motion will change. Anyone? So we should get a different equation of motion. Well, you all know the answer. We will find that the equation of motion remain the same. So what will change? It turns out, of course, then the tension being constant will change. If we relax this small displacement, well, as we will show immediately, we find that the equation of motion remains the same. This is actually very interesting because usually remember this wave equation is linear. And usually we will have this experience that the linearity comes only because of this restriction to small displacement. It turns out that in this case, actually the same linear wave equation remains valid, but then we have the tension of the string will no longer be a constant. It will change with the vibration. And so the T here actually will be different. Well, obviously, T will not be just the tension. Well, because if the tension is a function of time and space, then you can just put T here since C is a constant. And we will see later that the T here has to be replaced by the so-called equilibrium tension, the tension of the string when it is in equilibrium, when there is no displacement. Okay, so now we are going to derive the case when we relax this first approximation and then we derive it again. So that's more general. So let me just point out that I follow exactly the treatment presented in this paper. Okay, if you're interested, you can look it up. But let me show it here. Okay. Well, actually, it's good enough to use here. Yes. Okay. So, but let me switch to the whiteboard. It's easier. Okay. So remember, we have this picture again. But now we relax the condition that the displacement is small, and then we know that the tension can also be a function of time and space. So I will not use the constant. So let's just write it out explicitly. Okay, and again we have this angle here. And that is my theta 1. So same trick again, the mass, well, the Newton's second law. So this segment, I mean, the mass of this segment will be rho delta x, and we just say the acceleration is utt. Okay, this is uxt, and that is my ux. Well, so this is ma equals to the force, and the force will be t x plus delta x t sine theta 2 minus, well, sine theta 2, let's just be more specific, and I use also theta x plus delta xt. So that theta 2 is the theta at x plus delta xt. And this one is minus okay. And at the same time, we require that the horizontal component, the x component, the forces will add up to 0. So this is this. So it's the same equation as before, but now we don't enforce the small displacement or the small angle approximation. Okay, I should mention that this is probably not difficult to see. This equation I use here obviously only I'm thinking about the theta x or theta 2, theta 1 both being smaller than pi over 2. Otherwise, you have to turn the sign, but it will work out okay. So just want to say this. And because we don't have the small angle approximation, we have to relate the sine theta and cosine theta precisely to we used to relate to the tangent theta. So anyway, tangent theta, we know this tangent theta is u sub x, right? This is definition. The tangent theta is just the slope at that particular point. So to say tangent theta xt will be ux as xt. So I just drop the variables of the function. And so using here, and since I restrict to theta being less than pi over 2, then you can easily see that that would give me sine theta is ux over square root 1 plus ux squared, and cosine theta being 1 over square root 1 plus u sub x squared. Okay, so that will be very precise. We don't make any approximation, small angle approximation. And so now I use this and plug it in the equation. So let's just use them. Well, I have two equations. Let me label them. This is my equation 1 and this is my equation 2. So plug in the equation, from equation 2, I can get this. Equation 2 will imply, look at this. So this is exactly this function, right? You cannot see, I'm pointing. So this function, this product of t and cosine theta evaluated at x plus delta x and t. And the same function, the product of t and cosine theta evaluated at x and delta t. So I can imagine you divided by delta x, and that the left-hand side will be just the partial derivative, well, let's take delta x go to 0, will be partial derivative of this function, cosine theta, right? Cosine theta xt equal to 0, or precisely, I put in the cosine theta, by put in this expression, it will be this. Let me, okay, doesn't matter. So that will be the equation 2. And similarly, for equation 1, go back to equation 1 here. Again, I divide delta x throughout. I will have equation 1 implies rho u sub tt, and again divide the delta x throughout the equation and take delta x go to 0. Then you will see that this is also 1 x t. Well, I just be lazy. Well, you know t is a function of x and t, and then sine theta, right? And so these put sine theta here, it will be 1 x t u sub x 1 plus u sub x squared. Okay, it looks complicated at this point, so it will be far more complicated than before. Okay, but these are the two equations we get. So now focus on this one. 1 x of this combination, this product, or well, this whole thing being 0. So this whole thing has to be a function of time only. Okay, let me turn to next page. So that I will have 1 x, let me write down again, t squared root 1 plus u x squared, and this has to be 0, and so it implies t has to be 1 plus x squared equals to some function of t. But again, this function of t will only depend on the material properties, and so again, this will be just a constant, independent of time. For the case strings with whose material properties remains independent of time. Okay, so let me just make sure you get this. So now we see that this combination t, the tension as a place at position x and time t divided by the square root of 1 plus u sub x squared, this has to be equal to a constant. And what is this constant? Well, this is independent of time, so we just take it will be just a constant, and I evaluate this constant at the when the string is in the equilibrium position. When the string is in the equilibrium position, u sub x will be 0 because there's no u. Well, this u is equal to 0 and u sub x also equal to 0, and so in that case it will be just equals to a constant tension, the tension in the equilibrium. Okay, so this is the tension of the string when it is in equilibrium. So we get this new result. Let me just write down here, and then I'll explain a bit more. So we see explicitly that the tension of the string for the case of a general, well, not small, well, or large displacement will change as a function of position and also time, depending on the vibration, because it depends on u, or more specifically u sub x. So tension is a function of x and time, position x and time t. Okay, so it's not no longer constant. So that will be the new situation. But let us go back and see whether it will affect the equation of motion. Okay. So we have derived how the tension changes with time and space for the case that this displacement is not small. Let's go back, and that's the equation we have, right? This is the equation of motion. Remember I said it looks complicated before. So that's my 1 u t t equals to 1 x t with this combination. But t is just t0 times this square root of 1 plus ux squared we just show here, right? So this, just let me just write here, you'll see immediately. So this is t square root 1 plus ux squared. It's just t0, it's just a constant. So This combination will be just the equilibrium tension. So we can go back and we'll see that that's what we get for the equations. So this is just 1 x T0 u sub x. But T0 is a constant because this is just the constant tension that the string has when it is under equilibrium, when it is in equilibrium position. So that we can take the T0 out. Can you see? And then this is just u sub x. And then we'll just get the same result as before. So I will have u sub xx. I put the other things to the other side, rho over T0, u sub tt. And that whole thing is just my 1 over c squared u sub tt. And the c is just T0 divided by rho and the square root. The square root of T0 divided by rho. So we have the same form of the wave equation, but just have to understand that the T there is the equilibrium tension, T0. Okay, so let me switch back to the notes. So we find that the tension will change. So tension no longer is a constant, but related by this. We will use this result later, but when we will try to be more general in this course, it's more advanced course, and then we will just relax the assumption that the displacement is small. But in some sense, it's a surprise. We'll find that it is the same wave equation, the linear wave equation that we have seen before. But now the C is given by this T here is a T0. I use T0 for the equilibrium tension. So is it clear? Any question about this derivation, this more general derivation? Okay, yes. So let's see. I think it will be a good time for me to take a break of 10 minutes, and then I will resume. And okay, then when we come back, I want to discuss the solution of this wave equation. We'll quickly go through the solution, and we'll also do some examples. Okay, so my clock, in my computer at least, shows that it is now 5:22. So we'll resume, actually, well, anyway, 5:22, we'll resume at 5:32, okay? 10 minutes, okay? And well, you will basically study two cases. One will be the case for a string of a finite length, okay? And then the one is a general with no restriction, with the whole one-dimensional space. So we just solve the general one-dimensional wave equation next. For the case of a string with one finite length, so let me denote the string, and the length should be L. And so that's the wave equation we want to solve. And we to study the vibration of string, for example, we need to know the initial conditions. So, and in this case, we need to know the initial position, or, I mean, the shape, or if you wish, of the string, and also the initial velocity of different part of the string. So we have two initial conditions. U at time t equal to 0 for every point x being a certain function fx. So that function will be specified by the problem, and also determined by you if you set up the motion. And then the initial velocity will use up t, which is at each point x initial. So t equals 0 is given by this function gx. And for the case of the finite, the string with a finite length, then we also have two boundaries. Well, in this case, it's two boundaries will be just, well, we have boundaries, but these will be just two boundary points. And the two endpoints at x equals to 0 and x equals to L. So now we just consider the one common boundary condition, which is fixing the two endpoints. So boundary the two endpoints fixed, meaning that the string cannot move at those points, at those endpoints. So the displacement at those points has to be 0. So U0t and ULT has to be 0. So that whole thing together, the equation, the initial conditions, and the boundary conditions will specify this problem, which is an initial boundary value problem. And we solve this by the method of separation of variables. You should have seen this before, so we'll just go through it together. So the idea will be to look for solutions of this form that the separate being written as a product of a function that depend only on x and another function that depend only on time. So the function depend on x, I call it big X, and the function that depend on time is this big Y. So you plug it in, and then you, after put it, you can easily see that you can divide the whole equation by the product xy. Then you can write it as two parts. One part depend only on x, left hand side. The other part depend only on time, t. Since x and t are independent variables, then they can change independent of the other. So the two being equal must mean that each of them has to be equal to a constant independent of x and t. Okay, so now let's see it. Okay, if you learned it in your mathematics physics course, or the methods in theoretical physics 1 course with me, then you probably remember we have to check all possibilities. But now we're doing it in physics context, so we know. For example, we know that we're looking at vibration of the string. So these, this part, the 1 over y d square y dt square has to be equal to constant. This constant must be negative, otherwise it will not be a vibrational motion, right? And it will be negative omega square. As you can see, this is a well-known, familiar simple harmonic oscillation type equation. So we can immediately just write down minus omega square without going through all the the mathematical details to check, because we know in this case we're dealing with this vibrational motion of the string. Okay, so this part is easy. And then the other part will be this guy equals to minus omega square, but there's a c square here. So I put them together, and you will see this is an omega over c whole thing square. And I just call it k square. Omega over c is k. So k is equal to omega c. So at this point, k is just this constant being omega divided by c. You work out, you check the dimension, you can easily see that it has a dimension of 1 over length. And you will see immediately next that it is indeed the wave number of this particular mode of vibration. Okay, so now using the separation of variables, we separate the original PDE into two ODE, ordinary differential equations. And they are both of this very simple form that we can easily solve them. Second order linear constant coefficient, etc. Okay, but I just want to point out some terminology. So now I'm dealing with the one-dimensional version of the wave equation, but you can easily see that in the case of the general 3-dimension, then we will have to deal with this equation. This d2x dx squared will be replaced by the Laplacian. Okay, that's the equation for the 3-dimension. So this is the Laplacian x being equals to minus k squared x is the time-independent form of the wave equation, and it is called the Helmholtz equation. Okay, and k is to call the wave number, but we'll see also clearly why we call it the wave number. It is indeed, well, the wave number is indeed the 2 pi divided by the wavelength of the particular mode. Okay, so these two equations can be easily solved to be of this form: linear combination of sine and cosine of the corresponding variable x or t. And CDT, all these C, D, E, F are constants. And then, as you know, this x has to satisfy these boundary conditions. Remember, we have boundary conditions here. Both ends have to be 0. U at both ends have to be 0 because I fixed the string at those ends. And so you look at here. So in order for these two conditions to be satisfied at all time, t, for all times, then it means that x has to satisfy the two boundary conditions. X0 and XL has to be 0. Okay, so these are the boundary conditions also for X. So just to remind you, the equation, the boundary conditions together for X is this boundary value problem. Okay, and these boundary conditions are the conditions that fix the value of K. Okay, so fix the wave number or fix the wavelength for that particular mode. Okay, so put it in, then this one, because X equals to 0 has to be 0, then obviously this term vanishes at X equals to 0, but this term will remain, this cosine term will remain, and so this big D has to be 0. And you plug in then at this condition XL being 0, then you have to get that sine KL has to be 0, and that fixes the K. So Kn has to be n pi over L, and being any integer. But mathematically, you can also have negative n, right? Because this is sine KL for 0, you get. But in any case, the important thing is you see it does not affect the mode. So just restrict to positive n. So and then the corresponding, this Kn once fixed, again, it is fixed by the boundary condition. It will also fix the omega, the frequency of this vibration, because omega is being Kc, right? K equals to omega over C, so omega is K times C. And so omega is K times C, so it's n pi C over L. Okay, n pi over L, so it's n pi C over L. So now we have this particular solution, this form, the solution, well, is satisfied. Well, this particular, I said it's particular because it is a product of something that depends only on X and something that depends only on time. And the nice thing about this particular solution is the whole string vibrates at one single frequency, omega n. Okay, so if you recall from what you learned in your PHYS4011, what someone just asked me how, before the break, that how much this course is related to your classical mechanics 1. Well, we are classical mechanics 2, so obviously it is will be related to classical mechanics 1 in some way. So you should have learned your normal mode of vibrations in 3011, the classical mechanics 1, and the feature of normal mode vibrations will be the system, the whole system, all the components, all the masses in that case, will all vibrate at this one single frequency. Okay, so with this particular motion should recall you that feature, well, because the whole string vibrates at one single frequency omega n. So this is a normal mode vibration. So mathematically, we look for such special solution, they correspond physically to this normal mode of vibration. So we have this normal mode vibration, but since the equation of motion, that is the wave equation, is linear, well, remember here, it's linear, and also the boundary conditions homogeneous, 0. So then from what you learned in your 3051, the methods in theoretical physics 1, or you know that the principle of superposition holds, meaning that a linear combination of all these particular solutions, this normal mode of vibrations, will be a general solution. Okay, so the general solution will be, okay, I'm jumping ahead of myself, but in any case, general solution will be a linear combination of all these normal modes of vibration. So general motion will be a linear combination of the normal modes. Okay, so let's go back to the discharge of this normal mode of vibration. Well, there are infinitely many of them. Now, how do I know? Because there are infinitely many possible omega n, right? Remember, I find omega n from Kn, and Kn, there are infinitely many of them. So this should remind you that we are dealing with infinitely many number of degrees of freedom. There are infinitely many degrees of freedom. Okay, so that is exactly because we are dealing with a continuous system, not just, if you recall in your 3011 about normal mode of oscillations of a system of masses, then the degrees of freedom will depend on relate to the number of masses, right? The 3 dimension, then number of mass, you can do that calculation. But now we have infinitely many not normal modes because we have infinitely many degrees of freedom because of the continuum, right? There are many. Okay, but each of these modes is just of this particular shape. So the dependence of X is fixed, and then it just vibrates with time in a single harmonic fashion. So I just put up some examples for you here. And also you can see that the frequency will be proportional to n right here. And so they will be proportional n times a certain so-called fundamental frequency when n equals to 1. So that's just some terminology you probably learned in before. So this is the fundamental, this is also called the first harmonic and second harmonic, etc. So that will be very related to the musical instrument. For example, in the piano, the string, you try to strike the key and then you set the specific, well, in general, you set up a combination of different harmonics, but that's how it goes. And also here you see that this wave, this because it's 2 to n is note, so you have this wavelength. For example, here the wavelength will be half, twice this is half the wavelength. So the wavelength will be twice the length of the string, is lambda equals 2L, and KL will be pi. This for this particular mode. So you can see that indeed the K and lambda will be related this way. Kn is equals to 2 pi lambda n. Okay, that's how the wavelength and the wave number is related. Okay, so we are done with this. But then the linear combination, the general solution will be a linear combination of all this normal mode of vibration. And there are two sets of constants, this An and Bn. And they are fixed by the initial conditions, as you know. So we make use of, in this case, this sine function is being orthogonal, so we can easily get the coefficients. So the trick again is to multiply both sides by sine with a different m, and then integrate over x from 0 to L. Okay, and then make use of this orthogonal condition for the sine, and you'll get this. So for the full problem, we can solve exactly solve the problem, this initial boundary value problem of the vibration of the string, as this sum of the normal modes, and the coefficients are all determined from the initial conditions. Okay, so this is a sort of a quick review of how to solve the general vibrational motion of a string of finite length. Let me just stop for a second to see whether there's any questions. Okay, so we have talked about this condition, boundary conditions. We discussed this common form, which is fixing the two ends, and so the u has to be 0 there. So that is one type of boundary condition. Mathematically, this is the so-called Dirichlet boundary condition, fixing the function itself. But there are other physical situations for the boundaries, and let me just go to there. Okay, so first you can imagine you've not fixed the endpoint. I mean, not fix the string at the endpoint, but you control the endpoint to move at a certain fashion. And so in that case, you also specify the u, the function at the two endpoints, but it will be more general. So suppose you control it to move in a certain manner such that this u at 0 t at all time will satisfy this specified function f1t. Okay, so that's the more general endpoint control boundary condition. But another common boundary condition will be you don't specify how the endpoint moves, but you specify how the force, particularly the vertical force, the transverse, the force being perpendicular to the x-axis, the force, I call it vertical, along the y direction, specify the vertical forces acting on the endpoint. Okay, so I just call this force as F at point 0 and at point L. And then by specifying the forces acting on the endpoints, it will in turn specify the partial derivative of u with respect to x at the two endpoints. Okay, this is u sub x. So that shouldn't be difficult to see, but let me just switch to the whiteboard to show this. So I'm specifying, say, that's the endpoint at x equal to 0, okay? So I fix the force acting at this point, okay? So let me use different color. So I say there's a force acting on this point. I just call it F0t along the y direction. That's my y direction. And the vertical force due to the tension, that's the tension, it will be, remember this tension can be, I'm talking about the general case, so T can be a function of time. Actually depends on, okay. So, but this is my, say this is theta, right? So the force along the y direction will be T sine theta, well, T0t sine theta 0t, and plus F, right? And that has to be equal to 0. Why equal to 0? Because I'm talking about only one single point. For any single point, because the mass is 0, you know, this one point has no, you can imagine that there's no dimension. Well, I mean, no length, right? It's just a single point. So the mass of a single point is 0. And so you cannot have any you cannot have any net force acting on it. Otherwise, you have infinite acceleration. So any force acting on a single point has to, the net force has to vanish. Okay, so now let's just work out this. This, you recall that this is just, I just write this as T0, U sub x at T0T, right? Because now make use of the relation of the tension to the equilibrium tension that we derived before. And also actually sine theta is u sub x divided by 1 over 1 plus u sub x square root, and then the t. Okay, you remember what I have, right? txt is t0 plus u sub x square, and the sine theta is u sub x. So you get this, and so that just means, in other words, the condition will be specifying so if you you subject to endpoint to a certain specified force that can be time dependent, this F0t, then this is equivalent to a condition specifying the derivative of u sub x. So that's a Neumann boundary condition. Okay, and for the special case that this endpoint is free, so it's free endpoint. Well, free meaning it's not, there's no force, external force acting on this particular point. That it is free, then it means this F0t is 0 because there's no force, no external force acting on it. So that means this u sub x 0t is being 0. Okay, so endpoint, a free endpoint will have this boundary condition, u sub x being 0 at that point. Okay, so it should be clear. Or is there any question? So, okay, so that's for the endpoint x equals to 0. For the endpoint x equals to L, so I'll just do it here. Okay, well, imagine this is the endpoint L. Okay, and this time, then it's a little bit tricky, will be because it's like that. So you will see that the tension, well, again, the tension, I mean, the component of the tension in the vertical direction is still T sine theta, but then this sine theta will be related to ux with a negative sign. Well, you just work it out here. For example, here, then this theta will be larger than power of 2. So u sub x will be negative. So for the endpoint at x equals to L, the tension, the component of the vertical component due to the tension will be just minus t naught u sub x. But it really doesn't matter. Well, so for endpoint at x equals to L, then we have this. So again, if it is a free end, then this is equal to 0, then you still get the ux at that point being 0. Okay, so that's about the other type of boundary conditions. We will just mainly focus on 2 types of boundary conditions for the vibration of string in this course. One is the fixed end, the other is the free end. Nothing else. Okay, so let's turn back here. So just this is what I just showed you just now, but suppose you have a more general form of force specified. But in any case, if you specify the forces acting on the endpoint, then it will be, in general, it will be given by such mathematical expressions. U sub x at the particular endpoints being a certain function that you specify, and that will be so-called Neumann boundary conditions. But as I said, we will just mainly focus on the case of free end meaning no external force acting on the end, and so we have u sub x being 0. And one way to realize this is just to type your endpoint of the string to a ring, and the ring is very light, almost like massless. You can ignore the mass, and then it's free to move up. And you have also a smooth rod, so there's no friction, no force in the vertical direction. At least we will worry about the vertical direction. Obviously, you want to make sure that it is fixed there. There will be some horizontal force. So it's at the endpoint. So it's free to, there's no force acting on it in the vertical direction, in the y direction. And so it's free. Okay. And different boundary conditions, it should also be clear to you that we derived the general solution for the vibration of string just now for the particular case of the fixed endpoint conditions, boundary conditions. Okay, both ends being fixed. And that will be the boundary condition that determine the Kn, or the normal mode, the shape, the spatial dependence of the normal modes. So you should also understand that for other boundary conditions, the structure of the solution will remain the same as before, meaning it will be a linear combination of all these normal mode of vibrations, but the special form of the normal mode, particularly the spatial dependence of the normal mode, will be different. Okay, so precisely the solutions xn before, which is the eigenfunctions of the corresponding boundary value problem, they can be different depending on the boundary condition, and particularly the allowed wave number, and also the corresponding frequency, angular frequency, will also depend on the boundary condition. Okay, so that should be clear. Okay, so just to make sure you know everything is clear, you remember or at least understand what I just told you, I think it would be good to do an example. Okay, so that probably will be the last thing we did for today. But in any case, so look at example 1.1. So we want to study this vibration of a string, again, a finite length L. And now it is fixed at the point, the endpoint x equals 0, but free at the x equals to L endpoint. And we are given with a certain initial displacement, which is a function, which is just proportional to x. Okay, well, this is x. The initial displacement is x. That is the function I call f before is x. And then a 0 initial velocity. Okay, so I would like you to think about this. Well, it will be good for you to at least write down the equation of motion and think over it a little bit. So, when I instruct this course in a face-to-face section before, I will usually let the students try to work on example first, and then I will go to the solution. I think it will be good for you. Now with this online, it will be a little bit difficult. But before, I can see you, and I can, go around and check with each of you. But now I don't have this chance. But in any case, I would like you to at least spend a few minutes, think about this problem, and then I would go through the solution together with you. So at least set up the problem, okay? So here we are not given the equations, so you should at least understand the problem, write down the equations of motion and the initial condition and the boundary conditions. So I will give you a few minutes. Say I will resume in 3 minutes, okay? So now it's 6:01. I will resume at 6:04. Okay, so this problem, we are asked to, well, just let me write down so that you can check later from the video. So this example 1.1, we are interested in study this vibrational motion of the string. So we know that for the string, the equation, again, we let, it would be good practice to write things clearly. We let uxt be the displacement of the string. And so the equation that governs this motion is utt equals to c squared uxx. And then we also have the initial condition. Well, first the boundary at x equals 0 is being fixed. So we have x, this is equals 0. And then the other end is a free end. So we know that means u sub x lt is being 0. So that will be the boundary conditions. And then we have the initial condition saying that the initially ux0 is just x. Well, that's given to us, the initial displacement of the string. And then finally is the initial velocity, which is u sub t being 0, because we said that it's a 0 initial conditions. So these are the initial conditions, the IC initial conditions. So that these equations will fully specify the problem. And now we are going to just work out the solution using, again, the separation of variables. Okay, so that will be, we look for solutions of this form. And so you have this. Okay, so that's the standard technique for separation of variables. And so this has to be equals to a constant. As we said, we know that it has to be equals to minus omega squared. So again, that will be the thing we want. And so you get this. So basically, we immediately see that the y will be the same form. So don't worry about them. So as I go a sine omega t plus b sine, b cosine omega t. And then the more important thing will be for the x, but then here you see this x here will get this d2x dx squared equals to minus k squared x, k being omega over c. So you get again the sine and cosine. So let's just write here, not x, sorry. Then it will be sine kax plus d cosine kx. So what are the boundary conditions now? So boundary conditions from here that will be x0 has to be 0. And from there, it will be x prime at L equal to 0. Derivative dx dt, dx dx, sorry. And so we will have x0 being 0, we'll get implies d has to be 0. Well, x0 being 0 implies d equals to 0. And x prime L, then you just have sign left, and so there will be cosine KL, so K pull out. But so this 0 meaning that cosine KL being 0. So that will be the new thing, and that will means that K, well, K has to be of this form. Okay, so it's n pi minus pi over 2, and well, there's an L, right? KL. So I divided by it. Okay, let's just write L here first. So n from 1 to etc. So that will be the new thing. But other than that, the form remains, right? You still have sine kx, but then this is just a new wave number, and so a new corresponding omega. So let me just write down here kn being, well, if you wish, just write down un minus 1 pi over 2l, and so that will be my kl. And so the corresponding omega will be omega times omega that equals to kn times c. So let me just write here omega n equals to 2n minus 1 pi c over 2l. Again, one form. Okay, so that will be, then we know that we find all these normal modes and then we just add them up. So therefore, uxt is a linear combination of all these normal modes. So now we have this, and I have an sine omega nt plus bn cosine omega nt times that sine knx. But now just remind myself that k okay. So then well, now we need to fix these two constants, and we have to use the initial conditions. So this one and that one, okay? There are the two initial conditions. In particular, the second one, well, you will see u sub t being 0 for all, well, initially. Then we can see here immediately that u sub t, you just work out the u sub t. And that u sub t x t0 will means that, you know, only this term remaining. But this has to be 0. And so we have an being 0 for all n. That would be one thing. And then the remaining thing will be you use u x0 being x, right? So that will be summation n equals to 1. And just pop in xt equals to 0 here. And you get this is bn sine knx. So you have bn kn sine knx being x. And then you need to get the bn using this orthogonality properties of the sine. So you multiply both sides by sine km x, and then take the, you see this. So I have this precisely. Okay, so far so good. So that will be just the only thing you should get, well, essentially the same ideas as I showed before. It's just that now we have a special Kn different from because of the different boundary conditions. And also we have a specific x given to us. Before it's more general, the function. Now we just have to work it out. But this shouldn't be difficult. So you just leave it as an exercise. I'll just write down the answer for you. So you just use integration by part. You work on this and use the boundary conditions. And then you will see that this is equals to minus twice. Well, let me just write down for you. Kn square L. And then minus 1 n plus 1. And I plug in the Kn, use this Kn expression, then you can just get the, it should be like this, 8L 2n minus 1 square pi square. And then minus 1 n plus 1. So once I have this, then I'm done because I already, this is the solution that I should have. I'll be a little bit lazy, so I'll just do it here. And I now know that this an vanished. I already got this 0, so I don't have this term. And so I only have this bn, and the omega n, kn, I all know. It's already written all here. So the bn is just, that is my bn. So you just write it, well, of course you don't do it. Do not do this during your test or final exam. Write it clearly, but I'm going to be lazy. So I put all this in, then I'll get the answer for uxt. Okay, so any question about this example? It's just a review and quickly to make sure you remember all the details how to solve such initial boundary value problem. Okay, so also I'm very good on time, so now it's 6:15. So I'll just stop here for today. If you have questions, feel free to ask. So let me just go back to the notes, and then I will stop there.
Professor, I have a question on the notes.
Yeah, okay.
On the other boundary condition.
Okay, which one? So here.
A little bit upward. Here. So on the position x equals to